Welcome to Geology Boot Camp, where we get you thinking like a geologist before we get our hiking boots laced up. We're going to take a closer look at the tiny details and also step back to enjoy the view. So let's get started. Now, every rock tells a story. Some rocks are chattier than others, but every rock can tell a trained geologist a lot about the Earth. Rocks can be made up by 3 different processes, and the kind of rocks tell us what process happened in the vicinity sometime in the past. Rocks are made of minerals, which are made of chemicals. So looking at a rock can tell us about the chemistry of the interior or surface of the Earth, depending on where it came from. So how do we put these stories, which are pieces of evidence, into contexts of time and space? Well, let's start by answering that question by looking at a range of spatial dimensions of the evidence. Now, you can think of geology as the study of chemicals in their solid phase. Okay, so atoms of elements that are in their solid phase at the temperature and pressure conditions of the surface of the Earth bond together into a crystal lattice structure that forms a mineral. Minerals, in turn, are cemented together through geological processes into rocks. Now, rocks make up vast layers of rock that pile one on top of another, which form the tectonic plates of Earth and all the topography of our planet. Our planet is one of many rocky, gassy, and mini planets in our solar system, which is also made up of the solid phase chemicals. Okay? Our solar system is just a tiny portion of our galaxy, which contains millions of other planets and objects with solid phase chemicals. Okay, so you can see we're operating on many scales. So let's get back to Earth and look at examples of this kind of thinking in multiple size dimensions. In 2011, I was doing some field work near Dillon, Montana, and I came across a lot of specific kind of rock called Garnet Amphibolite. Okay, so here's a close-up look at an example of Garnet Amphibolite. As I was studying a piece of that was broken off by my rock hammer, I was working backwards in scale in my mind to work out the conditions under which this rock formed so that I could hear the story it was trying to tell. Okay, I was looking at the rock in my hand and I knew that I could see garnets in there. So I pictured a garnet and the kind of structure that mineral has. Each mineral is just a collection of repeating patterns of the same base unit of the crystal, which is called the crystal lattice structure. Crystal lattices are different solid chemical compounds that have been bonded together, like the silicon tetrahedra compound SiO4. And these, in turn, are all made up of elements like silicon, oxygen, iron, carbon. And once I was able to identify the building blocks that made up of the rock, I was able to take a step back and see the geological processes that formed that rock. Do you see the light and dark bands in this rock? That indicates that this rock was formed in a metamorphic process that at once reheated and squished the rock so that similar minerals could move around in the semi-melted rock, and then they bonded together into these bands as the rock cooled. So now I'm talking about processes that happen over large distances. To go from one rock to thinking about tectonic plates and continents, we need to remember that the very small piece in my hand that I was examining was chipped off of a much larger rock. A rock that most likely covered many, many square miles, and most of that rock was likely not even visible because it was under soil. In fact, all rock on our planet comes from these expansive and mostly invisible rock layers. The part of our planet that is directly observable is built on massive slabs and layers of rock. Here's a photo of the Grand Canyon in Arizona. It's a wonderful reminder of the massive scale these rock units can take. And the Grand Canyon isn't only a pretty rock collection, it's so much more. If a geologist was standing on the rim of the canyon and looking out over the expanse, they would see the beauty, absolutely. But there's more to it. Here's what a geologist might see after appreciating that gorgeous view. Most of these beautiful bands of red and orange rock were different sandstones in the Supai group, which are sitting on top of a pinkish red wall limestone near the Colorado River, and the Vishnu schist and the Zoroaster granite are visible from that river. Okay, each of these layers of rock represent a different geological process that occurred on this tectonic plate in the past. And each of these layers are made up of different minerals which reflect different chemical conditions on the tectonic plate when the rocks were formed. That's pretty incredible, isn't it? This kind of thinking not only adds knowledge, but I think it adds layers of appreciation and wonder to the beauty of this amazing planet that we live on. It's really easy to think of a rock as some small thing you can find in a river or hold in your hand. And it's easy to forget that rocks exist in such large scales that they can run for many miles in all directions. If you dig a deep trench and see a certain set of rock units, you should expect that the same general rock units are going to be a mile away in most directions, right? But rocks and geological processes are not always smooth, flat things. Okay, rocks can tilt, they can break, they can slide up or down relative to each other. Magma can break through small cracks in rock units and force its way up or pool in between layers. Or it can come in massive blobs and then slowly cool into these huge, strangely shaped things. Remember that rocks exist in the 3D world, and they exist on huge scales. We are very small things compared to rocks. Now, since we are so small compared, we often try to make simplified 2D models of what we observe to help us understand them better. So when we see a photo of rock units like this one, or a geologist's sketch of it, we have to remember that this is only a slice of the larger picture. What would it look like if we made a similar cut in the rock 20 feet into the photo? We don't know exactly because we can't see it from this image, but we assume that these rock units continue and have this shape and are not only present in this one part of the landscape. So looking at this image, we can see crumpled up layers of rock, right? Not only when we talk about spatial scales of these units, but we can also see backwards and forwards in time with our geologist's eye. Okay, so what do you think happened first? The formation of these rock units or the crumpling of the rock units? Okay, I admit it's kind of a silly question, right? But it illustrates how we can use these rock units to put together the history of an area. Okay, rocks do not form in a crumpled up way. Okay, this only happens when plate tectonics squish together, or when tectonic plates squish together and crumple up. So we know that there was some kind of plate boundary nearby and some kind of pressure. Now we're talking about the fourth dimension, time. Rocks, like humans, plants, and all other kinds of natural stuff in our world, exist in 4 dimensions. We have height, width, depth, and time. Don't forget about time. Rocks have a past and they have a future. Today's rock has been formed by all these past processes that it's been through. And our knowledge of the geological past tells us about the truths of the geological present, which will still be true in the geological future. This is one of the guiding principles of geology, and it is called uniformitarianism. Okay, I love this quote by James Dwight Dana from the Manual of Geology. In using the present in order to reveal the past, we assume that the forces of the world are essentially the same through all time, and these forces are based on the very nature of matter and could not have changed. The ocean has always had waves, and those waves have always acted in the same manner. Running water on land has ever had the same power of wear and transportation and mathematical value to its force. The laws of chemistry, heat, electricity, and mechanics have been the same throughout time. The plan of living structures has been fundamentally one, for the whole series belongs to one system, which almost, or as much almost as the parts of an animal to one body, and the relationships of life to light and heat and to the atmosphere have ever been the same as now. Okay, so with this idea firmly placed into our mind, never to be forgotten, right? Let's take a practical example looking backwards in time to get a better picture of the present. Okay, so let's go back to the Grand Canyon. It's a really cool place. See all those rock units and how they're all stacked one on top of another? Now the rock units at the bottom are the oldest, okay? And the rock units at the top are the youngest, like in a laundry pile. Okay, we can use minerals and geological principles to tell how old each unit is. If we look at other canyons in the north in Utah, right, we can see how the rocks are piled up there too and construct similar diagrams, which are called stratigraphic columns. Now this is taking a few 2D slices of geology and putting them together to get a more 3D picture. Okay, we can take a line between the sites and use those 3D columns. Okay. Where was I? To get a picture of what things look like. And if we were to dig really deep, deeper than the Grand Canyon, and get a really long trench and look at it, you can see the units at each of these 3 sites. Okay. But you can also get an idea of what happened back in the past. Okay, here are the 3 sites. All right, so schist only forms under high pressure, low heat conditions, which leads me to think that this unit formed when there was a collision of plates nearby, but not too close by. Okay, shale forms in deep ocean waters. Limestone forms on the continental shelf in the ocean, and sandstones form in shallow water. Nonconformities and disconformities and unconformities only form when rock units are above sea level. Okay, so looking at the Grand Canyon, we can see that this part of the world was near a tectonic margin where a collision occurred and then has spent time both as land and as ocean floor. Okay, as we can see in the order of the events in which these things occurred. Okay, one last note before I end the video. I want to introduce you to the idea of geological time. It is very different than human time. Professor Sorensen, I hear you say, but time is time, right? Well, okay, you're not wrong. But think about it this way. We measure time as it relates to our experience. We think of things in comparison to the length of a lifespan. My grandparents are old, and the stuff that happened back then is history, right? Well, okay, try telling that to a rock. Think about how long the lifespan of a rock is. Okay, a rock wouldn't see the difference between you and your grandmother. Rocks record history into the billions of years, whereas humans and human history and human memory records only the history of hundreds to thousands of years ago. Okay, geological time is vast, and it starts at the beginning of our planet about 4.6 billion years ago. Life didn't even start showing up in the rock record until about 540 million years ago. Even if geological time, or imagine that geological time was a clock, okay? Humans wouldn't even show up until the last 1/10 of a second before midnight, okay? Time is vast. The Earth is ancient, and we are but a small part of this planet in a solar system that is one of hundreds in a single galaxy in our universe. And our lives are less than a blink in and out of existence in this wonderful planet, twinkling like stars in the night sky. Just think about that for a second. I think it's beautiful.